Hello, welcome back to a Slice of Physics. We're now going to discuss capacitors and capacitance. We will talk about how capacitors are charged, how they store and release energy, and then we will discuss a property of the capacitors that's called capacitance, a word that sounds very similar to capacitors but it's different. We will discuss how capacitance depends on the physical properties of the capacitor and what its units are. Let's begin with two metal plates that are neutral and separated by a distance. As you'll remember from our previous discussions, this is a basic parallel plate capacitor. And when the plates are neutral, there is no potential difference between the plates. So in this case, if I write this as delta V across the plates, that would be 0. Now let me connect these plates to a battery. And as you know, the stub end of the battery is the positive end and the flat end is the negative end. And in the coming weeks, you'll learn more about batteries, and batteries essentially maintain the separation of charge using chemical energy that's inside the battery. These metal plates and these metal wires have free charges, meaning electrons that are free to move. So when you make this connection, the electrons that are held at one end of the battery don't like each other, and now you've given them an escape path. So they're going to use that escape path and get as far away from the other electrons as possible. So after a little while, you might end up with a couple of electrons that jumped to these plates to get as far away from the other electrons inside the battery. And then on the other end, you've got the positive end of the battery over here, which means it's got a deficiency of electrons. So the electrons that are in this metal plate that are also free to move will be attracted to that positive charge. So they'll leave the metal plate over here, making it net positive. And let's say the potential difference of this battery here, we call this delta VB, is 6 volts. So that's a 6 volt battery. So after I have had this charge separation that I've shown here, let's say that the delta V of the capacitor, delta VC, went to 2 volts. Well, the potential difference of the battery is still higher than the potential difference of the capacitor, so more charge is going to move. And this charge separation will continue until the potential difference across the plates of the capacitor equal the potential difference of the battery. So this delta VC eventually will get to equal delta VB, where delta VB was the potential difference of the battery. So if we started with a 6 volt battery, this charge separation will continue until the potential difference across the plates of the capacitor is also 6 volts. And once that's reached, equilibrium is established, so no more charges will move. This capacitor now is charged, and even though it's neutral in total across both the plates, charges have been moved from one plate to another to create a charge separation. So now I can even cut the battery off, and these charges are trapped on these plates and they don't have anywhere else to go. And because of that charge separation, there is an electric field between the plates that would be a uniform electric field, so it'll be the same everywhere between the plates. And because of that electric field, there is this potential difference that we talked about. This is how capacitors store energy. It's the electric field between the plates, because of the separation of charges, that stores electric potential energy, which gives rise to this potential difference. And then we can use that potential energy when we want by connecting something to it that can use that energy. So for example, now if I connected a wire with a bulb across these plates, I've given a path for all of these electrons to rush away from there and come and join these positive charges at this end, and that charge flow through this wire is a current, so that'll make this bulb glow. Now all of these electrons will rush very quickly, discharging the parallel plate capacitor, bringing it back to being neutral that we started with. So that very brief but strong current will make this bulb pop. And the common example of this is the camera flash. So when you take a picture with a flash, you see a pop of brightness for a very brief period of time. That's done using a capacitor. And when you take lots of pictures in succession using flash, you'll remember that your camera takes some time and says, I'm not ready for the next picture yet, and makes you wait for a second or two. What it's doing during that time is going back to the battery and charging up the capacitor. So this process here is called charging the capacitor, and that takes a few seconds because the battery can only work so hard to separate charges. And this process here is called discharging the capacitor, which typically happens very quickly, so we get a pop. Camera flash is a great example. Another very good example that's in the medical field is the defibrillators. So you've seen that when doctors shock patients to get their heart to beat again, they use the defibrillators, and then you have the medical technicians or the assistants telling the doctor to wait between applications on the patient because they're waiting for the capacitor in the defibrillator to charge back up. And then once it's fully charged, the doctor can utilize that separation of charge in a very quick discharge. Okay, so that's the basic of how capacitors work. And now I want to get a little bit more specific about how much charge needs to move in order to create a known potential difference. So for example, in this case, if I had a 6-volt battery, how much charge do I need to move between the plates in order for the potential difference between the capacitors to be 6 volts as well? That's where capacitance comes in. So capacitance is a property of the capacitor. It depends on 3 things. It depends on the area of the plates, and we call this A. It depends on the distance between the plates, and this is called D, lowercase d. And it depends on the material between the plate, or more specifically, the dielectric constant of the material between the plates. In our example, we just had air between the plates, but you can fill that with any insulator. You don't want to fill that with a metal because then it'll be constantly discharging as it is charging. But if you fill that gap with some kind of a insulator, insulators are dielectrics, and different materials have different dielectric constants. And this is written as Greek letter kappa. And this capacitance is written as C. And the equation form of this dependence is that capacitance equals kappa epsilon naught A over D. Let's look at the different factors here. Kappa is this dielectric constant. It's a property of the insulating material that fills the gap between the plates. And to give you some examples, kappa for vacuum is 1.0 exactly. For air, it's very close to 1.0, but a slightly larger number, so it's something like 1.0005. And for all practical purposes, we will use just 1.0 for air as well. And to give you a couple of more examples, Teflon has a kappa of 2.0, paper has a kappa of 3.0, and so on. So kappa is a number that's either 1 for vacuum or a number greater than 1 for other insulators. So higher the dielectric constant, higher would be the capacitance. A, the area between the plates, also has a similar relationship to capacitance. Larger the area of the plates, larger its capacitance. And smaller the distance between the plates, the larger the capacitance. So the closer the plates are, the higher the capacitance will be. And just to remind you, this epsilon naught is the same permittivity constant you have met before, which is a universal constant, and it's related to Coulomb constant as 1 over 4 pi k, which was the Coulomb constant is what appeared in Coulomb's law. This k is different from this kappa. Kappa is dielectric constant, Greek letter. This is English alphabet k. And this is equal to 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. I'm going to clear up some room in the top here to continue this discussion on capacitance. So what would be the unit of capacitance? Well, we can use this equation over here to derive the unit of capacitance because we know the units of all the things on the right-hand side. Kappa has no units, it's a unitless constant. Epsilon naught, as we just saw, has units of Coulomb squared over Newton meter squared in SI units. And then I've got area in the numerator, which would have units of meter squared in SI units, and distance at the bottom, so that would have units of meters in SI units. I can cancel this meter squared with this meter squared, and that leaves me with Coulomb squared divided by Newton times meter. Newton times meter is the unit of force times distance, and force times distance, as you have seen before, is work. Work has units of joules, same as energy. So this ends up being Coulomb squared over joules. And as a last step, joules is nothing but Coulomb times volt. You remember from our recent discussions that electric potential energy measured in joules equals the charge measured in coulombs times the potential difference measured in volts. So that's where that comes in. And one of the C's in the top will cancel the one C at the bottom, and this will leave me with Coulomb over volts. And that's the unit of capacitance. And I'm sorry for this double use of C. This C here is the unit of charge called Coulomb, and this C here is capacitance, which is the property of a capacitor. So the unit of capacitance is Coulomb over volt, but we give that a different name. We call it a farad. 1 farad is simply 1 Coulomb over volt, and farad is written as uppercase F. And just like Coulomb was a pretty large unit, farad also ends up being a pretty large unit. So a lot of times we'll use in real life situations things like microfarads, nanofarads, and even picofarads, where microfarads is nothing but 10 to the power of negative 6 farads, nanofarads is 10 to the power of negative 9 farads, and picofarads is 10 to the power of negative 12 farads. Okay, so we've seen how capacitance depends on the physical properties of the capacitor, but how is all this useful? Well, if I have a capacitor here and I had to separate a charge of plus Q on one plate and minus Q on one plate in order to achieve a potential difference of delta Vc across the plates, capacitance is the property that relates the charge separation to the potential difference. And that's the topic of our next video. In this slice of physics, we discussed capacitors and capacitance. We first saw that capacitors are charged by separating charges between the plates, and when you separate charges between the plates, that creates a potential difference across the plates. And capacitors store energy in the form of electric potential energy, which comes from the electric field between the plates. Then we learned about this property of capacitors called capacitance. We saw how it depends on the physical properties of the capacitors, namely the area of the plates, the distance between the plates, and the dielectric constant of the material between the plates. And finally, we discussed the units of capacitance, which is farad, and 1 farad is simply 1 Coulomb over 1 volt. In the next video, we will learn more about capacitance and how it relates to the charge separation between the plates.